As we talk about series and series convergence and divergence, one of the topics that we're going to be continuously bringing up is the remainder of a series. And so, what exactly are we referring to when we say the remainder of a series? Well, this is mainly associated with all of the convergence testing for series, because remember, we're doing these convergence tests for situations where, so in general, you're gonna have a series in a general situation. You've got something, in physics, biology, engineering, business, wherever in your respective field, you've got a situation where, let's say you've developed a sequence, you have a sequence, and you want to think about the corresponding series for that sequence. And so you put it into a summation like this to get the series, that you put the sequence into a summation like this. And if you're able to find the corresponding partial sum formula, the S of n, an explicit formula of n that's valid going from n is equal to the start point to infinity, well, then in that case, then you have everything you need regarding the series, because you can take that formula, take the limit as n goes to infinity. If it converges, then it's going to converge to a value, and that's the infinite sum. You've got the infinite sum. If it diverges, then the series diverges. But in regards to convergence testing, so the integral test, the comparison test, the ratio and root test, etc., the idea is you have a series like this, but you aren't able to get the S of n formula. And that's the case for most series. And so in that case, it's valuable, we've talked about this, it's valuable to test to find out whether or not the series is convergent or divergent, because if you find out it's divergent, then it's not like an applicable sum, like you can't really use that sum. If it's convergent, then, okay, yeah, you might not be able to find the exact value for the infinite series, but you still have an S of n here, the partial sum as a summation. So you can think about putting this into a computer code, like a MATLAB code, and plugging in n is equal to, well, you would do, okay, this is S, because we're going from, this is the infinite sum. So this is S, not S of n, just S, the infinite sum. But S of n, you could, since you have the A sub n, then you could get the S of n as a sum, as a summation. You just do this, right? And so, yeah, you might not be able to find S, the actual infinite sum, but you can come here, put this into a computer code, and plug in n is equal to 5,000, 5 million, whatever, to get an approximation for the infinite sum. Okay, and so I've talked about this in a previous videos. That's the main purpose, at least for non-math majors, of convergence testing. Because you would, before you get an approximation for the sum, you'd want to test to verify that for sure it's convergent. So for sure it's convergent, then you go ahead and say, okay, well, let me just take n is equal to 5,000 or 5 million and get an approximation for the infinite sum and use that for my application. Okay, but now as we go through these sections on convergence testing, in each of the sections, what we're going to talk about is, can we get an estimate for how accurate the partial sum that we've used is? So if we chose n is equal to 5 million, how accurate is that? And we do this by studying what's called the remainder of the infinite sum. Okay, so note that this remainder idea is not like just part of the integral test or just part of the comparison test. The idea of the remainder, R sub n, this is just a general property of any infinite sum. Like you have an infinite sum, then you think about the infinite sum, you think about a partial sum, and then with that you can think about the corresponding remainder. So the remainder is just a property of an infinite sum. And for each of the tests for convergence and divergence that we study, we're going to look at, for that specific test, how can we analyze the remainder? So what is the remainder? Because this could be kind of confusing. Okay, so let's start with the infinite sum. Here's the infinite sum. Okay, S, not S of n, just S. This is the infinite sum. We're assuming that this series is convergent. So when we're talking about the remainder, we've already found that the series is convergent. Okay, so this is a convergent series. And so since it's convergent, we can say this is equal to S. We couldn't say this is equal to S if it was divergent. But so it's convergent, so this is equal to S. And so let's go ahead and go from this form and write this out. Like there's different ways you can write series, and you could do it in that expanded term by term form with like 3 dots. Like, so let's do that. Okay, so we can write the infinite series as a sub 1 plus a sub 2 plus a sub 3 plus ... Okay, and we can write it this way. We can write it any form we want, but one way we can write this, that I think you'll agree, is that we could say to a sub n, okay, and then plus a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3. You should agree that this is a valid way of writing the infinite sum. We could just put plus then ... after a sub n, but this is just another way of looking at it. Okay, now S sub n, the partial sum of this infinite sequence, we write as, and this is so a sub 1 plus a sub 2 plus a sub 3 plus, and then we stop at a sub n, right? That's S sub n. And so you can see the way we wrote the infinite series is the S sub n here, a sub 1 plus a sub 2 plus a sub 3, all the way to a sub n, and then plus all of the other terms going to infinity, right? The idea of the partial sum is you're summing the first n terms of a sequence. And we're thinking about an infinite sequence, so S sub n, you're summing the first n terms of an infinite sequence. So the way we've written the infinite sum here is the S sub n, and then plus all the terms that we didn't include in the infinite sum, because we only took the sum of the first n terms. Okay, so with that, what you can see is we can think about the idea of subtracting S sub n from S. So we take all of this and subtract it from this. And what we're left with is, so S minus S sub n, we're left with what we call R sub n. And that's, you can see, is a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 all the way to infinity. So this is R sub n. It's the remainder of the infinite sum that you didn't include. You took an infinite sequence and you summed the first n terms. But in doing that, you omitted summing the terms after n in that infinite sequence. Those terms you omitted is called the remainder. And the remainder is the infinite sum, S minus S sub n. Again, we're assuming this series is convergent. If it's not convergent, then we can't do this because we can't say this is equal to S. Okay, now, so what you can think about is it's of interest to analyze R sub n when we're going to use, for the case where we can't find an explicit S sub n, and we're going to use this formula to get an approximation for the infinite sum. It's of interest if we have some information about the R sub n, the corresponding R sub n. Why? Because think about, like, you could have your code that you put this into to get an S sub n. And so if you put this in, and you might say, okay, well, I'm going to do n is equal to 5,000 or 50,000 or 5 million. But wouldn't it be nice? Ideally, what would be nice is if you could say, you don't input an n into the code, you input a percentage of accuracy that you desire. Like, you can't get the exact percentage because we can't ever, if we could get the exact R sub n, then we'd have the infinite sum. But we can only get approximations of the R sub n, but you have like an upper limit on the accuracy though. With that approximation of the R sub n, you could say, I want to know that the S sub n that I use is at worst 0.5% off, 0.1% off, whatever, at worst. Well, then you could put in that 0.5% and it would calculate the corresponding in that needs to be used for you in the background. And you get a value. And so that's ideal. Now, if you, for some reason, you don't have much information about the R sub n, it's not the worst thing in the world. Just put in a big in. But if you're doing an approximation like this of an infinite sum, ideally you have you know about the R sub n of that corresponding partial sum, right? Okay. So as we're going through the different convergence testing methods, for each of those sections, we're going to, for that test, we're going to analyze the R sub n, because for each test, you're going to have a different way of determining the potential, the range of the R sub n, of what the R sub n is. The integral test has one way of analyzing R sub n. The comparison test has one way of analyzing R sub n. Okay, now just note what this is, that you input an n, right? Like for the S sub n and the R sub n, you have the same input. So I would say I've got an infinite series, and I would say S sub 5,000. And that's saying the sum of the first 5,000 terms. For the R sub n, if I also input R of 5,000, what am I saying? I'm saying sum starting with the 5,001 term of the sequence all the way to infinity. That's what I'm saying, which is going to be convergent, because the series is convergent. So think about what this is saying. It's the same. It's the same input into both of these, but they have two different meanings. Okay, and note that just like if you have an S sub n like this, if you see an S sub n, you know that that's intimately tied to an A sub n, right? That's the whole meaning of an S sub n. It's intimately tied to an A sub n. Well, in the same way, if you have an R sub n, that's intimately tied to an S sub n, because it corresponds to it's the remaining terms of the, like the S sub n. Well, okay, the S sub n is intimately tied to an A sub n, which if it's an infinite sequence is intimately tied to an S, right? And so then the R sub n is kind of, these are all tied together, with the heart of it being the A sub n. You start with the A sub n. And if it's an infinite sequence, then you could think about the S of that A sub n if you put that A sub n into a summation. So if you have an infinite series, then you can think about an S sub n corresponding to an infinite series, but an S sub n doesn't have to correspond to an infinite series sum. You could have a summation that goes from n is equal to 1 to 1,000,000, because the sequence only goes to 1,000,000, and then think about the S sub n for that, going from summing S of 100, let's say. But if we're thinking about an infinite series, then you've got the infinite sequence A sub n you put into summation. If it's an infinite summation, you have an S. So the S sub n in that case is intimately tied to the A sub n, and since the A sub n is infinite, it's intimately tied to the S. Then the R sub n, I guess you could think about an R sub n for a non-infinite series, but we're really thinking about it for infinite series. The R sub n is intimately tied to the S sub n, because it's what's remaining that you didn't include in the infinite sum or the full sum. Okay, now the last thing I want to talk about on this topic is, so when analyzing the R sub n for a series based on some convergence testing method, in general, you can think about it like we're going to want to get an upper and lower bound on the R sub n, right? Because, okay, we're thinking about this R sub n, it's like a number. It is a summation. It is a sequence. Like S sub n, you can think about as a sequence. It's like it's another sequence corresponding to A sub n. But it's also like a sum. Same thing with R sub n. R sub n has the similar properties to the S sub n, but it's like a number too once you plug in an n. And so this is depending on the value of n. Depending on the value of n, once you input an n, you have a number. So what's the upper and lower bound on that number? And that's how you could, with those, once you have that, then let me do this, once you have that, then you could determine, okay, it's the worst case percentage error, which you would get by comparing R sub n to S. The worst case percentage error is this. Okay, but another way you can look at it, and we're going to see in problems, they talk about how you can improve the accuracy of your partial sum estimate is, okay, if we add S sub n to this entire inequality, so each part gets added S sub n. Well, R sub n plus S sub n is S, right? And so if you add S sub n to each of these, what you get is an upper and lower bound on S, on the actual infinite sum, right? And so with that, what you can think about, a trick that you can do is you have the approximation you calculated, but a more accurate approximation would be just the midpoint between this, the midpoint between this S upper and S lower. So you could just take whatever estimate you got and replace it with the midpoint between these two. And that increases the accuracy a little bit. Okay, so that's the remainder of an infinite sum.